Hello community, so great that you are back. Quantum AI is an absolutely fascinating topic, so let's see if we start from my last videos how fast we can approach there. You remember we had a look here at test time compute scaling, reinforcement learning, reinforcement fine-tuning, we looked at CRL, we looked at off-policy, Luffy methodologies, and it was great. And you see in one of my last videos when we talked about multi-agent learning, I told you, yeah, it's great, yeah, but this is not an elegant solution. Because if we have to treat every token here as an action in our token level multi-agent reinforcement fine-tuning methodology, this is rather complicated, especially if we code it, no? So what would be here an alternative? Alternative would be if we go here with some basic ideas that we have from theoretical physics. And in this video I showed you how to build a Lagrangian and Hamiltonian. We looked at very simple introduction from MIT and how we have our AI physics. Now, you know, months ago we already talked about swarm intelligence in a multi-agent ecosystem where you do not have a central agent that commands every other agent. And we ask here a swarm intelligence. Now, this would, especially in a multi-agent system, in a heavy multi-agent system, this is what we are looking for. And now the question for today is, how can we combine all of this? And if you look closely, you see the solution is already visible. Because, do you remember, and in the simplest case we looked at, PPO objective and reinforcement learning, we looked at here the canonical objective function for PPO, for our reinforcement learning methodology. And it was the easiest we could find. And I told you, whenever we look at reinforcement learning, this objective that we have is always there. And usually we talk about here expected reward functions, no? Where we have our agent policy, P theta is tuned to maximize here a cumulative reward. And if you listen closely, you saw in my last video here, supervised fine-tuning optimization here, multi-agent, we have the same in supervised fine-tuning. In supervised learning, the objective is typically here a loss function. And you notice, this is our classical SFT, we have a cross entropy, and we have also an objective functions. So you say, interesting. So if we have in both cases, everything that we know in AI is about an objective optimization. So what about we stay with this, but we just advance it a level. We go a level harder, further. So in both cases that we know, we optimize here our J of theta using here a gradient descent. And yes, of course, we will go for a stochastic gradient descent that you know for centuries now. So objective optimization refers here to a process of adjusting the parameters or the behavior of an AI system, of a learning system, in order to optimize, either minimize or maximize, a well-defined objective function J of theta. So this objective now quantifies here a performance criterion, cost, reward, utility, depending what you want. Here, for example, reinforcement learning, we had a reward function. In supervised fine-tuning, we go with a cross entropy in the loss function. Beautiful. Now, if you remember, in this one I talked about physics. And if you know a little bit about physics, you remember Emily Noether here. Noether's second theorem relates a symmetry of an action functional with a system of a differential equation. And just a short fresh up, this is real Wikipedia. This is the simplest explanation here. If we have an action S of a physical system, of a real system, a real world system, so if action S is an integral of the so-called Lagrangian function L that I showed you here in this video, from which the system's behavior can be determined by the principle of least action. You learned this in school. This is here our most dominant nucleus, if you want, in physics, in astronomy, astrophysics, wherever we are. This is the nucleus for us to mathematically develop the laws of physics, the law of nature, whatever we find. Principle of least action. And the theorem says that if the action has an infinite-dimensional Lie algebra of infinitesimally symmetries parameterized linear by k arbitrary function and their derivatives up to an order of m, then the functional derivatives of our Lagrangian satisfy a system of k differential equation. And this is the way we developed here, if you want here, all the laws that you are familiar with. Think about equation of motion. If we have the sun and the planet Earth, if you have here a black hole and a neutron star, we have now a complete physical understanding in our laws, in our mathematical, about equation of motion. This is exactly what we do in special relativity. We even find those symmetries down at a quantum level. So this is a real powerful theorem. But we are still missing one idea, no? If you are a subscriber of this channel, you say, yes, of course, I remember. We were talking about here a system dynamic case where we had a very specific message passing here. And yes, of course, we are talking here about graph neural networks. Now, message passing, we had a look here at Deep Graph Library. We looked at here at the Keras coding of a graph neural network. We looked at multi-agent topology, DSPy, but we also looked at the next step, if you want, no? Topological message passing on a graph neural network. And we saw, hey, we can make it even a little bit more interesting if we go to simplicial complexes here on CW networks. And I have even a video where I go another step further, but we don't need this for today's video. So here we have it. We have physics, we have our swarm intelligence, and then what we do not want is, we don't want to have here at first this buffer that we have here currently in our latest AI research on multi-agent reinforcement fine-tuning. We want to get rid of all these buffers. We want to get rid of here the central critique agent. We want that this system develops here locally. We have here an intelligence that's from the ground up, develops here in the complete system, propagates through the complete system here. This is what we are looking for. And you remember, even in this video here, the multi-agent RFT, I told you we need further experiments to explore here the multi-step for the benchmarks in coding, but especially on agentic tasks, because this seems to be rather complicated. We need to find a more elegant solution. So what do you think? We start here with three basic ideas. We focus here on autonomous self-learning system without a central intelligence. So in multi-agent speak, it would mean no orchestrating agent. And we will focus as the driver, we look at theoretical physics and our current AI, and we say, we will focus here on objective function. Of course, now it will be a little tiny bit more complicated. Then we will stick of one of the guiding principle in AI that was so helpful, and we will try to hold on, at least into the first development step, to a partial observable Markov decision process, especially when we do reinforcement learning. And then comes the beauty. For purely mathematical reason, we need a completeness theorem, never mind. But now we say, hey, we want that this starts to develop locally. We don't want that we have an external input from some ground AI that is really closed up by OpenAI, really expensive. No, we want to have this from a local base that the whole system develops. We go to the next level in the AI system, and we want to build, therefore, an axiomatic theory. And those are the three elements. We don't want anything else, maybe a little bit of complexity theory, maybe a little bit of functional graph theory, maybe a little bit of theoretical physics, and a little bit of mathematics, but this is it. And I will show you the final result. You should see what comes out today. So let's have a look. We have a tool set in AI. Remember, if we do here any optimization backpropagation, we have the tool of a stochastic gradient descent. And I will notice here, or stress here, stochastic gradient descent, because we will come back to this idea. This is really powerful. Maybe we can hold on to it. Maybe we just have to modify it a little bit. And then whatever we have in supervised fine-tuning, reinforcement learning, test time compute, scaling reinforcement line fine-tuning, and multi-agent reinforcement fine-tuning, this is nice, but we saw, especially in the last videos of last week, they have so many limitations going further. So, what do you think about stochastic gradient descent? Yes. What you think about, yes, and you know this from the Atom optimizer that and yeah, it was an update of RMS prop, and this is beautiful. We had the momentum methodology, and this is all great, but this is all past. Let's look in the future. Let's have a look what we want. So here in this synthetic AI image, you immediately recognize, hey, quantum computing. Finally. So if we say we will have quantum computer in the next years, maybe it's 5, maybe it's 10 years, never mind. We have to have a theory that fits here to our, if you want, infrastructure. Because what we have currently in quantum computing and currently what we have in AI theory, oh heaven's sake, this will be a pure catastrophe. This is not gonna work. There are so many much more elegant solutions to this. So let's do both. We develop AI and we try have a look here at quantum physics, quantum computing, quantum field theory, and let's say how we can modify that the tool set that we have here on a code base fits together with the infrastructure and we have a win-win situation. It's coherent. The final result, this is it. All of what we have today and all of what the latest AI research is, this is what we will develop today. And it's a major step forward. What we have is now, we will stick to our objective. No? Our objective function will become maybe a little bit more complicated, but never mind. And we will move here in our AI idea from a neural network structure and a tensor structure and matrix multiplication. We will move now to a little bit more intelligent field approach. But it will be an intelligent stochastic field. And you say, this is the connex. No, yeah, absolutely. We will have a local, decentralized, and it will be defined over transition, and not what we have currently in our reinforcement learning actions. So you see, we go up a level in the complexity, but this opens up new tools in our toolset that are so much more beautiful. In our field, we will have nodes. We will integrate here this graph theory much more intelligently. So for each node that we have, we will define the local operator, a gamma operator here from a very particular Hilbert space to R, and we will have here with H. Gilder, we will have here the space of the state transitions. So we move now here to a higher complexity level where the theory describes not just states and actions, but we move now to our transition theory. And if you know complexity theory and you know a little bit of quantum mechanics, you know exactly where we're heading. And our gamma assigns now a reward. This is our classical reward. This is identical what you know to a transition that will affect the node X. You see? Absolutely simple. And then we defined here an objective function, like I showed you in physics, the least action principle. Our Lagrangian, we will develop a Hamiltonian view on this. So we will have an average objective here at the node X. Here is our gamma bar, and gamma bar will have this particular form, and there's a specific reason. And I will show you that this integral has also a very specific feature that resembles here quantum mechanics. And this is the reason why we do it. No? We want to have coherence in the theory. So we will talk now about here state distribution in our system. We will use here operator algebra that is a little bit, not in that simple Hilbert space that you know, but we will lift here the Hilbert space here to an advanced space. We will define generators. We will define here linear generators. We will break it down to infinitesimal generators to operate here in an algebra on particular transition, and the transition itself will be rather special from a mathematical point of view. And then we have an integration, and the integration will give us exactly what you know. We will have here now the time average cost or the reward that is associated with this transition. So you see, we are back here into an optimization problem here as in AI today. It's just that the quantity that each node holds and aims to minimize. And you say, hey, wait a minute, so each node minimizes now? Yes. This is why we introduce here intelligent fields. And this is just done by adjusting here an operator, a generator, a local generator. And yeah, there is a little bit of mathematical proof that we have to show, but this is it. This is the new idea. And it's so familiar. It uses all the old ideas that we already have today in AI. It just develops it a little bit further. It adds exactly what we need to have a much more elegant theory, a more powerful tool theory. So let's start. Intelligent field. Aren't they beautiful? exactly. Our fields are more of a pure mathematical nature, no? And you know this. So we start with a unified formal framework. It's a purely mathematical framework. That's why I do this video, to give you a beautiful introduction that you feel familiar with these terms. And it is for an objective-driven, you see again, like the least action, objective-driven that we have in RL and supervised fine-tuning. It will be dynamical, of course. We want to have a time evolution. And it will be a stochastic field. And you say, hey, I know this, no? And I already told you about the 3 axiomatic principles. And the beauty is now we can do this in pure mathematics. So we will have a complete configuration. We go with a Markovian time invariant evolution in a finite configuration space. We will build on this space later on. And we have a locality. And this is beauty because this is now, we will have local features and this will interact only with its neighbor. Let's say on a directed graph, if we build a Hamiltonian space on a graph structure, and it will be just constrained by the graph topology that we will implement here. And in plus, and this is here the most powerful idea, the most beautiful, the most elegant idea, purposefulness. And this is exactly what I meant here with objective functions or defined objective values. So we go like in physics with the least action Hamiltonian, Lagrangian function. We go with the equation of motion and everything. So we are real similar to what we know here, if you want, in mathematics and physics, and AI finally comes over here to a little bit more advanced theory, no? That gives us better results, better implementation. So you see, this is it, 3 points. This is all there is with this intelligent field, in my introduction, of course. So we have a continuous time stochastical field, and now we have 3 aspects, and it's the same. We have the field aspect, the dynamic aspects, and how we do this purposeful with a goal-directed update. And this is exactly our J of theta that you know from reinforcement learning and supervised fine-tuning. So a spatial graph structure, this will be the base where we build our Hilbert spaces. We have a local dynamic, a local stochastic dynamic, of course. We are talking here about probability distribution in the dynamics. And we will have the, if you want, overall goal here for the complete system to optimize itself to achieve a better learning. This is all that we need. The stochastic dynamics will be defined via an infinitesimal generator and operator, and the purposefulness, and this means the local objective and the signal propagation that you are familiar with, no? With message passing here, for example, from a graph neural network, we will add here a little bit more far-reaching components here on an operator that I'm gonna show you. So we will propagate our signals here via a linear, the simplest form of a propagator operator. So let's have a look at this. Summary. Intelligent field, what we have, it is simple. We have a directed graph, this is the base, this is our spatial topology that we build upon. Then we have local configuration spaces omega. Now you know our omega is a little bit more complicated than the spaces that you know from the classical AI theory. Then we have local operators, local generators G of X, specifying here the purely stochastic update rules on our omega, given here a specific configuration. Then we need, of course, here the big picture, so we need a global generator, and this will be a rather complicated mathematical proof. I'm not going to show you that we can build this in this particular way in the simplest case. Then we have objective operators, you remember, the least action here in physics. Gamma X defining here the local transition cost. This is here, if you want, our optimization theory. Then, of course, we need here for the far-reaching interaction, like a gravitational field here that penetrates here more or less the complete universe, that we have a signal propagation that maps here our operator, so that weaves here our local objective into a coherent global objective. And you see here immediately where our multi-agent interactions come into place, but now in a mathematical, much more elegant solution. And then we go with, you notice that gradient descent. We have the same, from the name, the same gradient formulas, enabling now each node to compute here this, if you want, gradient descent using here only neighbor information, but of course we are operating in a completely different mathematical space with completely different mathematical operators, and it is not a gradient what you imagine, but you see, in principle, this is what we know and this is what you're going to build upon. A little bit more that you're now familiar with all of this. So we will have locally defined objectives that propagate now across the graph. And each local rule that we define by our generator balances now exactly like you know from reinforcement learning. I told you we always have exploration, this equilibrium here, and exploitation. So exploration will be our stochasticity, and the exploitation will be our objective minimization optimization problem. So globally now the collective effect guides now the system towards, if you want, trajectory. It's a little bit different, but in the simplest case, it is a trajectory that minimizes here the total action. You remember from physics, this is really the same principle, abstract idea, the least action principle in physics, and now we build an AI theory that is based now on this beautiful theoretical physics insights. And you know what? The local gradient and this beautiful propagator mechanism now enables here the complete system for decentralized learning. We don't need to have a main intelligent agent that directs here the task to the specific worker agents. Now we can implement swarm intelligence on a much more powerful, a little bit more challenging mathematical idea of AI. So now that we had a look, what is a field? Let's have a look at the node, because I think the node definition is here also something that I was struggling a little bit to understand with. So what exactly is this node? A node is a labeled point in a finite directed graph X. Couldn't be easier, no? Now, it defines here a spatial structure of this field. So it presents an entity that holds now a local configuration W, omega, at a specific time, at a specific node. This entity, think about graph neural network, interacts only with its neighbor. The node connects via edges in the graph, and it defines here a local stochastic process. So we do have a time continuous, careful, it is not a discrete anymore, we will go here with an integral formulation, a time continuous jump process that updates its own state, and perhaps some outgoing signal. Remember, we are working with partially observable Markov decision processes, depending on the current state of itself and the neighbors. So this is classic, this is graphs, you know this. So it's the same guiding mechanisms. It's a little bit technical because a node is not a vector, it's not a tensor, it's not any numerical quantity per se that you know of the classical AI, of the legacy AI. It is a location in the graph that hosts now a stateful stochastic mechanisms. And it has a dynamic, it evolves by applying a local operator, or g of x, to a global field configuration. So this is now where the dynamic picture comes in, and I think we have to look at this a little bit more. But what's happening here is finally we make the move from AI today to, and guess what, to a level where Schrödinger was. You remember his cat, Schrödinger's cat? And Schrödinger formulated this in the 1930s. Can you imagine? 90 years ago, we had the same state of development in theoretical physics. And now, today is the first time that we say, okay, let's make this jump. Let's make this jump here. Imagine Schrödinger coined the term quantum entanglement in 1935, 90 years ago. And now we try to move AI into the quantum area. And it is so beautiful that we can use a lot of the ideas from Schrödinger, from the development of theoretical physics. And at the end of the video, we will look at Feynman integrals that we can finally apply here, because we will use path integral formalism to bring us a little bit closer. No? So, a little bit more detailed look. So each node in our intelligent field now has a local state space that we have to generate to have our operator algebra, for example. No? So we have an omega, and we have now, and this is partial observable Markov decision process, we have an internal state in this node. It's a simple two elements, two divided structure that we build. So we have an internal private state of the node. Let's call this M. And then from graph neural network, we have to signal out, message passing and everything. And the node is sending this out to its immediate neighbor or two-step neighbor, three-step neighbor, and you get the idea. And this is called A. So the full local configuration omega at a particular time and a particular node consists now of an internal discrete state, so a final set of mode of counters, whatever you have, and a collection of outgoing messages signal, one for each outgoing edge. And the global configuration, omega, is now the full tuple of all the omega at a particular time for a particular node over all possible x. Simple, no? But careful, you see what's hiding here? Partially observable Markov decision process. So elegant, and we know how to use this from the classical AI. Now we need a dynamic in this system, no? And you know what we do? Stochastic field dynamics. We go the beautiful way that we know. So we have a global configuration. Omega of t evolves over time to a continuous time Markov process. And you immediately see, all the other or L methodology, they were not continuous. And now we're gonna make this a continuous time Markov process. And we need, of course, here a generator, and we need a linear generator. And if we really go down, we need an infinitesimal generator, g of x, that defines here the probability distribution over omega. And it gives us here the time development. And you see here, beautiful, here this is how our g is integrated in the system dynamics. G from a omega dash omega gives here the transition rate. So we move here from a particular state omega to a state omega dash. Now, this is not trivial here. There will be a mathematical proof. G decomposes here as a sum of local generators under some conditions where each g of x acts only on this particular node x and its neighborhood. So this makes now life much more easier for us because node x controls only g of x. So the transition rates for those parts of the field configuration that it can affect are now locally defined. And you say, isn't this great? This is what we wanted. Short summary. So for each node x, we have a label position in the graph. It holds a local configuration omega, sends and receives signal. Remember, message passing in graph neural network to and from the neighbor. And it evolves asynchronously. Important, yes, great, fantastic. Via local stochastic jumps that are defined by the operator g of x. For the transition rates here, our generator defines how the node x configurations stochastically change over time, probability distribution, depend on its current state and the defined neighborhood, and the quantities that get optimized, and now again by our least action principle of physics, our optimization of the local objective function gamma bar. This is it. So you see, the evolution is governed here by local generator g of x, which defines how the configuration jumps from one state to another. And we have a stochastically asynchronously jump. And now, at the time I had a question. I said, so wait, so each node in the field now has its own operator g of x and its own local objective generator gamma bar? And reading the paper a second time, it turns out, yeah, exactly. So g of x, if you want a transition law here, defines how the node behaves in our intelligent fields. So its current decision-making process, the stochastic rules by which it updates its configuration in reaction to the neighbors, in reaction to the message passing that happens. And this g of x will change during the self-learning process, or the learning process in general. Gamma of x is now, careful, our objective function, remember? So this gamma of x defines now what the node values, no? So the objective, our optimization, is trying to minimize it over its own transitions. And this is what we define at the beginning, and this will remain fixed. So what we achieved is now a self-adjusting, highly dynamic system where the node has now a dynamic in a mathematical operator algebra that is just amazing. And this will open us the interaction to multi-agent system. So, if you want, this is an important sentence. Given here a gamma of x, the node adapts now its specific g of x to minimize here the long-run cost gamma bar that are associated with gamma of x. This is exactly what we know from, if you want, the classical AI. This is exactly reinforcement learning, supervised fine-tuning. We have the minimization problem. We have here defined here a specific objective function. And we have now an adaptation, not of the weights of a tensor structure in a layer of a transform in the classical AI system, but now it adapts here an operator in a Hilbert space, in a lifted Hilbert space. Yeah, so it is similar. Just remember, this is here. Think about this. In reinforcement learning, we have the reward function that depends on the state, on the action here. And this is like our gamma of x here. And the policy function here that we used here, our pi theta, again, action and state, is learned to maximize the cumulative reward. And if you want, if in a mathematical abstraction, this is our operator g of x here. You see, we just make it a little bit more higher dimensional to achieve a better, more elegant theory, that we have better understanding and more capability of handling those objects and have a better, higher dynamic that we need, especially for multi-agent system. Yeah, there's... Okay, now it becomes a little tiny bit more complicated, but this is just why we have mathematics, and mathematics tells us, hey, careful, there is something, but never mind. So when you compute now the gradient, you know our stochastic gradient descent, this is almost the same gradient. In the long run average cost or reward, if you want, like, you need to account not only for which nodes propagate your perturbation in the system, but also when and how long the effect lingers. And this is now handled by the resolvent operator. And you remember this equation? Yes, of course. And it appears that inside the propagator, there's a specific form and we have different terms. And Q injects an immediate perturbation at some node. S here propagates the perturbation forward in time across the stochastic dynamics. Our G Gilde now translates it back into the effect on transmission rates. And then, we have a pi that projects onto the stationary components. But this is not so important if you don't really want to calculate this. But what's now interesting is that these two mechanisms, the iterated local propagators here, or P, was the spatial hubs, and the resolvent for the temporal spreading, you see, they give us a full spatio-temporal propagation function, an operator, to be clear, that carries now the local objective to all parts of the field over all the times. And you say, hey, wait a minute, is now path integral? Yes, this is exactly why we do this. Then to finally open up now and come a mathematical theory that we can use our insights from quantum mechanics and quantum field theory. And you know what? It fits. Isn't this amazing? The physics or the ideas that we have, how to develop the laws of nature in the gravitational fields, what holds the universe together, what holds our galaxy, the stars together, the Earth orbiting the sun. The same laws, if you want, are also applicable to a new form of AI. For me, this is really interesting, but maybe you don't share here the same enthusiasm. I absolutely understand it. But think about it. This is important. Spatial hubs, temporal spreading, fully spatio-temporal propagation function that carries now our local objective, if you want, our local learning, our local gradient perturbation, now with an operator to all the parts of the field of all the times. And guess what? We are there. Let's talk about the Hilbert space. Now, you are familiar with Hilbert space in physics, no? So, original Hilbert space, we start with a finite configuration space, and Hilbert space, the basis vector corresponding to a single configuration, omega, you know this, and a vector represents your probability distribution over omega. This is the classical AI, no? And for all our state level dynamics, we bring in the dynamics. We have here a beautiful differential equation, and they all live here in this original Hilbert space. Now, if we go this step now, we need a little bit more complicated Hilbert space that is a little bit more powerful. So we call it the lifted Hilbert space, and the vector in H tilde now can represent any function of the current state and the next state. And it's just a tuple. It's a tuple that we know from reinforcement learning. We have an action and a state, and now we have a state-state transition tuple. And this transition form and operator now lives not in the simple Hilbert space. It would not be powerful enough, but now we need here the lifted Hilbert space. This is H tilde. Easy, isn't it? I told you, it's going to be a beautiful introduction. And they called it lifted because we have lifted our attention from a single configuration to a pair of configuration, and thereby evaluating the mathematical arena so that we can define and manipulate transition level objects. And this can be everything, objective, impulse, gradient, in a fully linear algebraic way. The mathematics is easy. So why we need a lifted space? If anybody asks you why we operate now in H tilde, you say we need to assign cost or rewards to a particular transition probability, to a particular transition from omega to omega dash. And how we do this and how we calculate the transition now becomes interesting, because we will have an evolution operator that propagates not a complete system from a time, let's say 0, to a particular time t. And this evolution operator now tells the system now how a distribution evolves over time according to the dynamics that is included here in our local operator, in our, if you want, global operator G. Now in theoretical physics we use here a specific mathematical notation to indicate here, going back to Schrödinger here, the probability amplitude. And we have a specific notation, and this is it. So we have here a probability amplitude that would, or a probability density that shows us here if we go from omega 0 to an omega at a time t that we call omega dash. This is exactly how we note it, how we calculate it. And this is an inner product that computes here the probability density that's starting at a configuration omega at a time t equals 0. The field will arrive at a configuration omega dash exactly at the time t that we're interested in. And this is, if you want, the quantum mechanical analog to a transition amplitude from omega to omega dash. Look at this beautiful equation. Isn't it gorgeous? Can you identify the terms? Yeah, this is our Feynman notation. Great. And then we have here the action functional that is associated here with particular paths. Here, this simply means integrate over all trajectories that we found in our configuration omega at a particular time t. And then we have here a path integral, the sum over all stochastic paths in our transition. And now it's so important that we operate now in the right Hilbert space, because we go here from transition to transition. So we have here to include this in our operator. So look at this. So this integral involves now all possible trajectories, the intelligent fields, if you take it here from omega to omega dash during the time t. So what does it include? So you have infinitely many random jumps, stochastic. You have a continuous stochastic evolution, and you are focused on the local interaction. Only the neighbors matter in our graph structure, and this will then propagate for a particular time and a particular strength to the complete network. So why do we need now a path integral here? Is it that we want to enforce it here, or does it emerge naturally? Now, instead of looking here at a step-by-step transition, the path integral encodes here the entire evolution over time in a compact and mathematical powerful form that we know how to handle from theoretical physics. And this is critical because in continuous time fields, many tiny stochastic jumps happen, and computing each one would explicitly be just crazy. And this is where now our quantum compute possibility, theoretical possibilities can come in, because this is exactly why we need this coherence. The path integral formulation enables now our variational approach, our variational methodology. How does a small change in the dynamics of the operator g of x affect now the expected cost or the expected reward? And the variation of the action now yield gradients with respect to the operator g of x via our operator techniques. And this is essential for the local gradient formula that we're going to apply for the optimization of the complete system. So you see, without this particular approach of a path integral, we would not systematically compute how the long-term cumulative behavior depends on the local transition rules that is defined in our operator g of x. What an elegant, beautiful solution that we found. Now, let me be clear. I have a little bit of a theoretical physics background. This is not Feynman yet. This is not quantum, pure quantum yet. This is an approach in the right direction, and maybe there is something missing. But let's have a look what we have and what is still missing. So, if we compare now what we know from theoretical physics, our Feynman integral, and let's go with quantum mechanics here and AI intelligent field, this new AI approach. Both use functional integral over the paths of the function of times. And this is great. Both assign here an exponential weight to each path depending on its action s, and this is amazing. I just showed you the formula. Both express here this particular evolution operator, this is one in theoretical physics and this is the one in AI intelligent field, as integrals over all possible trajectories. What a coincidence, because we started, this was our game. And now we have a problem. No, we are still not there yet. Let's formulate it. So in physics, Feynman, if you see his lectures, you have complex phases, and of course this is beautiful in theoretical physics, leading here to inference pattern, and remember the double slit experiment. You remember this, there was something, no? But here now in our intelligent fields, because we are so simple in our first approach for AI, quantum AI, we still operate with real weights here. And this reflects here a classical stochastic probability theory. No problem, no, I have ideas. Yeah, but for the moment we stick here with this simplification. So you see, it's not there yet, but we are on the right way to have a coherence finally. So, path integral naturally appears when we want to express probabilistic evolution over all possible trajectories. Finally, it encodes the long-run behavior of complex, local, stochastic interaction, compactly and analytical, complex not in a mathematical term, but here in the complexity given of a particular task term. It generalizes here, it simplifies here, it orients itself at the Feynman construction from the quantum mechanics to stochastic dynamical systems, and finally over continuous time Markov fields, and thus the appearance of the path integral is not arbitrary. It is really necessary. It is even kind of fundamental on an axiomatic way if we want to have this idea of an intelligent field model that is now able for some decentralized learning, for some dynamic, for some evolution, and even in more complex reasoning paths. So this is here one beautiful new idea that I think will lead the way. And you might say, but that was simple. This is all there is? Well, guess what? Of course not. This was just the introduction to warm you up, because the real beauty is here. We have here Professor of Stanford University and a genius, a PhD student of Stanford University, and they, I know it's a week old, they talk here about a framework for objective-driven dynamical stochastic fields, and you know what? The text you see here is just on the first page because we have 44 pages of pure mathematics. But I wanted to enable you to understand the main idea, because if you read now this paper, you will be excited about it. And if you still have some problem in understanding, I have a particular video here on AI mathematics here. So this is now a screenshot of some of the pages. At the very first, the simpler pages here, and you see exactly what I have been talking about. Configuration space of a field here, the locality, what we talked about, the infinitesimal generator, how we can decompose it here with the locality principles, commutative relations here. Now, finally, in a beautiful mathematical proof. Here, then, the path integral formalism, maybe, if you're not really into it, it might be, yeah, so this is why I do this introduction video. And then, decomposition we have here, we can build our Lagrangian, beautiful path integral formalism, completing here the generator formalism and limits and whatever. So, I tell you a secret, the first time I saw it, I thought, is this for real? Is this really happening? And you know what? I went back and I checked the two authors. I just wanted to make sure they are a real person at Stanford University, because I thought, if this is generated by the AI, you know, just as, I don't know, April 1st, but no, it is real. I did not expect this at all. I'm absolutely amazed by the idea. I have so many additional ideas now. I'm starting to read the paper. It will take, I guess, my complete weekend to read the paper. But yeah, it looks really absolutely interesting. And you know, even for the simpler cases. Look, this is what they write here about reinforcement learning. Yeah? And they say now, the reward mechanism is quite complex, as each agent now both generates rewards for the other agent in the system and also receives now rewards from them. So this is beautiful. Now we have a dynamic in the reward structure that we don't have to wait here for one agent to have a final reward function and then, I don't know, a +1 or -1 or 0 or whatever you go for, a binary reward signal, and then we go to the next agent. But we have a dynamic, highly interactive system. And even if you just look at it from this perspective, my goodness, how much it could improve theoretically here the classical reinforcement learning perspective. Now, I have to tell you, this is pure mathematics. This is the first approach. There is no code implementation, because if you read this, it will break your brain. And you know what? You might ask, hey, is this now a solution that is elegant enough for you? And I would answer you, I'm so glad that you asked, because I have new ideas how we can further build on this idea. And you know what? If we just add the following elements. End of part 1.